I just figured out that I didn't record with the voice now, so I'm just kind of go over on top of the video I already made it. So for section 2.1, we're going to start talking about the area between curves. So the exam 1 is talking about we have R is a region bounded by the graphs. You can see that I'm using a decimal to graph it. And there are two functions, f of x, which is equal to x over 2 plus 5, and the g of x is x plus 1 half. And we're going to do it over the interval 1 to 5. From the decimal, I graph both functions. And decimal is a really nice tool for us, will help us for this section. So I graphed the first one, y equal to x over 2 plus 5. And since we only want it for the interval from 0 to 5, so I restricted, only want the decimal to show me the piece from x equal to 0 to 5. And then I also graphed the y equal to x plus 1 half for the same thing over the interval x between 1 to 5. Then what is the region R? The region R is going to be the region between those two lines, which is the shaded region on the graph or on the screen. And here we want to find the area between them. But we know that in order for us to find the area, we're going to using the integration. But for integration, we can only find the area between the curve and then the x-axis. For example, for the first one, y equal to x over 2 plus 5. And if I do the integrations from 1 to 5, then this is the area I'm able to calculate it. So the integral from 1 to 5 of x over 2 plus 5 dx, which give me the area of this red shaded region. Now if I do the same thing for the second function, y equal to x plus 1 half. And the integral of y equal to x plus 1 half will give me the area of this shaded region. But you can see that none of them are the ones I shaded originally. So how can I find the region I wanted here, the region R? I can subtract them. I can subtract the larger area minus the smaller area. In other words, I can subtract the pink area minus the blue area. So to set it up, we're going to using the function on the top minus the function on the bottom. And we're going to integrate them from x equal to 1 to 5. So the area is equal to the integral from 1 to 5 of the top function x over 2 plus 5 minus the bottom function of x plus 1 half dx. So that is how we set it up. After that, we can just go ahead and calculate the integral. So integral 1 to 5, x over 2 plus 5 minus x minus 1/2 dx. Simplify them. X over 2 minus x, which is negative 1/2 x. And 5 minus 1/2, which is going to be 10 over 2 minus 1 over 2, 9 over 2. Using the power rule, is going to be x to the first power become to 1/2 x squared. And 9 over 2, the constant, will become to 9 over 2x. And then we will evaluate it from x equal to 1 to 5. And we got negative 1/4. 5 squared plus 9 over 2 times 5 minus negative 1/4, 1 squared plus 9 over 2 times 1. I like to have parentheses to group them so I know the first part is evaluating the original function at x equal to 5, and the second part is evaluating the original function at x equal to 1. Now we can simplify them. And we got negative 25 over 4 plus 45 over 2 minus negative 1/4 plus 9 over 2. Where 45 over 2 becomes to 90 over 4. So that's how I got 65 over 4. And then 9 over 2 become to 18 over 4. So that is how I got 17 over 4. Adding them, I got 48 over 4, which is equal to 12. Let's move on to another example. So again, I use decimal to graph the two functions, so we can see a nicer what is the region looks like. So we have two functions, f of x equals to x, which is the red straight line, and then the polynomial g of x equal to x to the fourth. Now, this problem didn't give us the interval, but from the graph, we see that the two functions are intersecting at those 2 points. So the region we're looking for is where the two sections are intersected, or the enclosed section, which is the one we had it on the screen. So the areas is going to be from 0 to 1, because that's the two parts we have that when they intersect. And then the top function is the red one, y equal to x. The bottom function is the blue one, y equal to x to the fourth. Now we can integrate them using the power rule and evaluate it from 0 to 1. And we ended up with 1/2 minus 1/5, which is 5/10, minus 2/10, which is 3/10. Be careful that when we evaluate it, we're only evaluating the x. So that is why it's 1 square instead of 1/2 square. And same thing is 1 to the 5th power instead of 1/5 to the 5th power. Then just in case you do not know, for somehow you do not have the decimal, or for somehow you want to draw them by yourself, you do not know where they intersect, you cannot see them, then you have to calculate where the intersections are. To find it, you're going to set the two equations equal to each other. So for this case, it's going to be x equals to x to the 4th. And you're going to solving them in terms of using factor. You cannot divide it by x. So when you factor it, you got x times x cubed minus 1, where x cubed minus 1, you can using the difference of cube formula to get it as x minus 1 times x plus 2, x squared plus x plus 1. Where x squared plus x plus 1, if you try to solve it, it will never equal to 0. So you have x equal to 0 and x equal to 1 as your two intersection points. Now we have another one. For this example, we have trig functions, sine of x and the cosine of x. And it's over the interval pi over 2 to 2 pi. So using decimals, I graphed them with the restricted domain pi over 2 to 2 pi. You can see that that's the graph. So it's supposed to be very straightforward. However, we do see that this graph is two pieces. The one on the left, the red line is on the top. The yellow one is on the bottom. However, for the graph on the right, the blue one is on the top. The red one is on the bottom. So if we're going to using the top function minus the bottom function to find the area between them, we do not know which one to use. So for this particular problem, or for this type of problems, we have to thinking about there are two different areas, and we're going to finding the two different areas separately. And in order for us to know what is the regions, we have to figure out what is the two lines they're intersecting. So that is why I set it up equal to 0, equal to each other, sine of x equal to cosine of x. And I know that when x equal to pi over 4, sine of x and cosine x will equal to square root 2 over 2. But this is the only value in quadrant 1. We also have another value, x equal to 5 pi over 4, which is in quadrant 3. Both sine of x and cosine of x will equal to negative square root 2 over 2. In quadrant 2 and in quadrant 4, sine and cosine will have opposite sign. But since we are talking about from pi over 2 to 2 pi, we are talking about quadrant 2, 3, and 4. So the two graph will intersect is going to be 5 pi over 4 in quadrant 3. So the area is going to be the first area plus the second area. For the first area, it's going to range from pi over 2 to 5 pi over 4. And then we're going to using the top function minus the bottom function, where the top function is sine of x, the bottom function is cosine of x. For the second area, it's going to range from 5 pi over 4 to 2 pi. The top function is going to be cosine of x, and then the bottom function is going to be sine of x. Okay, so this is normally how you're supposed to do this type of problem. You're going to calculating the two different areas or even the three different areas by themselves and then adding them together. However, for this particular problem, this is a special problem. Number one, we have a trig functions. Trig functions are periodic. Number two, by looking at the graph, we know area 1 and area 2, those two shapes are symmetric. And because they are symmetric, they will have the same area. So I do not need to calculate the area twice. Instead, I can just do a 2 multiplied by 1 of the area. Because area 1 is the first area, so I'm just using area 1 and just multiply the result by 2. So the derivative of sine, the antiderivative of sine is negative cosine. And then the antiderivative of cosine is sine. And then we're going to evaluate it from pi over 2 to 5 pi over 4. Where cosine of pi over 2 is going to be 0, and sine of pi over 2 is going to equal to 1. And we already calculate that cosine of 5 pi over 4 is going to be negative square root 2 over 2. So negative of negative become to positive square root 2 over 2. Same thing for sine of 5 pi over 4, which is a negative square root 2 over 2. So negative of the negative become to plus square root 2 over 2. And minus 0 minus 1, which is going to be negative 1. So it becomes to plus 1. And square root 2 over 2 plus square root 2 over 2, that is 2 square root 2 over 2. 2 square root 2 over 2 times 2, which is 2 square root 2, and then 1 times 2 is going to be 2. So the answer is 2 square root 2 plus 2. So decimal is definitely very useful for these sections, finding the areas, and make sure that when you have multiple pieces for the area, you're going to finding them individually and then adding them up.